Welcome back. We are continuing our lectures on power series. That's our third topic in AP Calculus AB. Today we're on to our very last Taylor series, or rather Maclaurin series, that we need to memorize. And we're also actually going to learn what the heck a power series is. I mean, we're in the power series unit, so we might as well learn that at some point. You've been asked to memorize 4 Taylor series, though a Taylor series can be centered at any value. We've actually been memorizing Maclaurin series, which are Taylor series centered at x equals 0. Let's go ahead and list those 3 series you know by heart, including those general terms. So take a quick second, pause me, see what you can do. All right, hopefully you've got them all. If you didn't, I'm going to remind you what they are. We have e to the x. We have, I usually like to start with cosine of x. And last but not least, sine of x. So if that helps jog your memory, then pause me again and give that a shot. And if you didn't need the help, then you can just make sure you did it right. E to the x, 1 plus x squared over 2 factorial, plus x cubed over 3 factorial, plus, and then of course we get our general term, x to the n over n factorial. No problem. Second one, cosine of x. Remember that cosine is an even function, which means it's only going to have even exponents. And the easiest one to start with is x to the 0 over 0 factorial. We're considering 0 to be an even number. Last but not least, sine and cosine always alternate in sign. So my next one is minus x squared over 2 factorial plus x to the 4th over 4 factorial, and so on, so forth. I don't know why I wrote just x to the 6th twice. I think you get the idea. And then, of course, we do need our general term, a little bit more challenging. We know we go by 2. And it looks something like this. Checking really quickly, if I replace x with 0, do I get my 0th term? I do. Nice. Last but not least, sine is an odd function, so we use odd terms. It also alternates in sign. No pun intended with sine and sine, but you get the idea. And I think our general term is also not that bad. It is going to use, oh, and I forgot something from the general term up there, so I'll leave an extra space. Still going to be something pretty similar to this, but if you replace n with 0, you do not get 1. You need to add 1 to each of these. And I forgot my alternating factors. Silly, silly. There we go. Ha! All right, we do need to know these 3 by heart. Well, I guess you don't have to, but it does make your life a lot easier if you do. You're going to save minutes on your exam, which is actually a lot considering that every minute counts. Okay, the last series that you're going to be asked to know will originally seem a little bit random. E to the x, cosine, sine, all those make a lot of sense because they're transcendental functions. We don't know how to calculate them without a calculator, but this is easy to do without a calculator. Cool. We are going to explore why this function is useful in the future, and we'll see a little bit today, but much more on when we come back to this. So for now, we're going to create the Taylor polynomial for f of x equals 1 divided by 1 minus x, centered at x equals 0. Or if you want, it's the Maclaurin polynomial for f of x equals 1 over 1 minus x. So how do we do this? Well, we have f of x, and we really need to go through until we find a pattern. So we get 1 over 1 minus x, which, because I know I'm going to have to take the derivative, I'll bring this up to the top. So it's 1 minus x to the negative first. Okay, and then I'm going to go ahead and actually I'll probably find all the derivatives first. That might be a little bit easier, and then we can find their values underneath. So f prime of x, I'll use this guy right here, and I should alternate colors so we can keep this straight. So f prime of x is going to be negative 1 minus x to the negative second. Or if I do need to use this at some point, it's negative 1 over 1 minus x to the positive second. Continuing to move through, let's look at the second derivative of x. This becomes 2. Wait, I've made a big oopsie here. I definitely forgot the chain rule, so I brought the exponent down, but I forgot to multiply by the derivative of the inside, and I read that over here. Don't forget the chain rule. I'm like, what chain rule? That chain rule. The 2 negatives multiply and turn this back into a positive. Ugh. Okay. Third tries the charm. So really what I have then is I have the equation positive 1 times 1 minus x to the negative second. Okay, here we go. Third derivative. Nope, second derivative. Oh man. So the second derivative of x, using this guy over here, is going to be negative 2 times 1 minus x to the negative third times negative 1. But can we see now that these are just going to cancel each other out, save a little space here? 2 over 1 minus x cubed. Do we have a pattern yet? 1 over 1 minus x, 1 over 1 minus x squared, 2. We might start to realize what's happening, but I think it could also take us an extra derivative, so let's do our fourth derivative as well. Nope, third derivative as well. So negative 6 times 1 minus x to the negative fourth, but really we get an extra 1, so it's positive 6. So 6 over 1 minus x to the fourth. Do we see the pattern yet? We originally started with 1 and we multiplied by 2 to get 2. Now we have 1 times 2 and we multiplied by 3. And then we're next one going to multiply by 4. Couldn't we rewrite the numerators as factorials then? Oh yeah, buddy. So if we're looking at this, I think one way we could simplify these terms is f of x equals, and then let's do this with factorials here. The numerator is 0 factorial, right? And the denominator is just 1 minus x to the first. So then my first derivative becomes 1 factorial over 1 minus x to the second. And then I think we could find a whole bunch of these really, really quickly, couldn't we? Right? My second derivative becomes 2 factorial over 1 minus x cubed. That is my second derivative, isn't it? Yep. And then my third derivative becomes 3 factorial over 1 minus x to the fourth. And let's just go one more for fun. The fourth derivative of x will be 4 factorial over 1 minus x to the fifth. Cool. And if we wanted to go out further, we could. It's pretty easy once we have the pattern, but let's go ahead and actually write this Taylor polynomial, Maclaurin series. Is there a color I haven't used yet? Not really, so we can go with black. So 1 over 1 minus x is going to equal, I should write smaller, I'll need both lines here. Okay, is going to equal, and then our normal pattern, f of 0 over 0 factorial, x minus 0 to the 0th, f prime of 0 over 1 factorial times x minus 0 to the first. Look at that trifecta again. Keep that triangle going. You'll be just fine. The second derivative of 0 over 2 factorial, x minus 0 squared. And we'll do one more just for fun. Like so. All right. And then we should probably do a little plus, plus, plus. And then I think I have enough room over here to start simplifying things down. So f of 0. We're going to have to do a little mental math here, but it's not bad. If you substitute in 0, I think f of 0 is just 1. So we get 1 over 1 times x to the 0th. And then f prime of 0, if we substitute in 0 over here, I think we get 1 as well. So plus 1 over 1 again times x to the first. The next one, f double prime of 0, plug in 0, we get 2 over here. So 2 over, but then 2 factorial back here is 2, which again reduces to 1, but we can reduce that later on. And then my next one, we are going to be over 3 factorial, and the third derivative is 6 though. So we get 6 over 3 factorial, 3 times 2 is 6, x cubed. Notice that the factorial that's happening on the top is canceling the factorial on the bottom. And so, again simplifying, we get that 1 over 1 minus x is actually equal to, here's my first term, which is just 1. My next term, x. Next term, x squared. X cubed. Wow, this is actually really easy, because then I think my general term is just x to the n, and now we have our very last Maclaurin series Taylor polynomial that we should memorize. 1 over 1 minus x is a very easy function to memorize if you center at x equals 0. However, we should probably make sure we did this correctly too, shouldn't we? To check to make sure we did it correctly, we're just going to graph each one of these and make sure the graphs start to match up. So we have our first one, 1 over 1 minus x, makes this rational function asymptote at 1. And we said that the Maclaurin series is going to be centered at 0, 1, right? So it has to be, they have to share that point. And so my Maclaurin series is 1 plus x, tangent line, plus x squared, quadratic line, quadratic curve, plus x cubed, plus x to the fourth, plus x to the fifth. And it's an interesting one because this does a really good job of following our function, but it looks like it stops following the function after -1 on this side, and then it never wraps around to join this function over here. So I can keep adding terms, and it looks like it's going to get closer and closer to this function, but it never passes that -1 barrier, and it never passes the +1 barrier. So this is actually one of the first Taylor polynomials we've looked at that isn't going to perfectly match the function forever, though it will perfectly match my function f of x at least from -1 to 1. And we're going to go more in depth on this about why our function is matching in only a small interval here as opposed to the entire function, but that's a lesson for another day. All right, now you're going to try two more based on the same series above. Okay, we should actually find two interesting things about this Taylor series. And I think you should be able to go through and do this no problem. If you want a hint though, right, my hint here is that you're just multiplying by 2. So all I think that's going to do is take every derivative and multiply the derivative just by 1, 2. That 2 is a constant. Or if you're going to multiply every derivative by 2, isn't it just going to take every coefficient and double it? So in this case, I really think we don't even need to do any work here. It's just going to be 2 plus 2x plus 2x squared plus 2x cubed plus 2x to the n. That's pretty darn quick. Look how fast we just created a Maclaurin polynomial just by knowing what this series was. Or of course, if it was -3, then switching colors, we would get pretty much the same thing, I think, but now everything's multiplied by -3, which just causes our Maclaurin series to look slightly different, but nothing too bad. Right? And really, I should put minuses here, huh? Be a little bit more accurate. Cool. So two things to note here. The first is the obvious one. What do you notice about the two series above when compared to the parent series of 1 over 1 minus x? Well, it looks like they're just multiples of that, right? What does that suggest you can do with series? Maybe that you can multiply by constants, which really opens up a pretty big world of functions, but we're going to get more into that later on in the future, not today either. But the fact that we know some pretty darn important series and that we can multiply the actual series by a constant, well, that tells us then that now we don't just know 3 functions, we know an infinite number of functions. If I want 2 cosine x, just multiply everything by 2 and life gets a lot easier, right? So this opens up a whole bunch of functions just by having to memorize 4. However, the most important and the trickiest connection here is how do these 3 series above relate to another infinite series we've seen before, right? In particular, I'm going to show you the parent function, 1 over 1 minus x, right? Isn't this 1 plus x squared plus x cubed, so on and so forth? Don't we have an a value of 1? And a common ratio of times x every time? What do we call a series with a common ratio and a starting value of a? Isn't that a geometric series? Geometric, apparently I'm great at spelling. Go me, I picked the right career. Yeah, and actually, if we didn't know this, and we saw this as a geometric series, didn't we learn how to find the sum of a geometric series? Didn't we learn that it was the first term divided by 1 minus the common ratio, or in this case, the first term is 1, and the common ratio is x? Look at that! This is that geometric series that we learned in our last unit, and when you find the infinite sum, we've now proved that the infinite sum adds up to 1 over 1 minus x. That's just a different way to show that this is indeed the Maclaurin series, right? We derived it using our knowledge of Maclaurin and Taylor series, but also once we got there, we realized it's a common series we knew before. It's a geometric series, and the sum of a geometric series is like so, and it shows that they match. And this is super huge. This connects something that we've learned for the last entire unit in 2 different ways. And that is why the Taylor polynomial for 1, or rather this should say the Maclaurin polynomial for 1 over 1 minus x is known as the geometric Taylor series. We're going to finish today by actually talking about power series. And we're going to do that to try to relate everything we've done so far back to our unit on infinite series. So let's begin. A power series is defined as any series that fits this format, where we say it's p of x. So this is a function of x. There's going to be x in here, where we have x minus a to the n. And this x minus a to the n tells us that this is a series centered at x equals a. So just by looking at the formula, you should be able to see the center, opposite of a if you'd like to think. And it also has some sort of coefficient. Now, what that coefficient looks like is dependent on the series. If you wanted to start to write out a few terms in this series, it starts with n of 0. So we replace n with 0, and it says the 0th coefficient, so some coefficient, x minus a to the 0th power, plus, because we're summing up our series, then a different coefficient, c sub 1, times x minus a to the first, plus another coefficient times x minus a squared, and, of course, so on and so forth. So again, c sub 0, c sub 1 are standing in for different coefficients. Well, doesn't that look like, of course, this type of series resembles Taylor series? However, in Taylor series, right, c sub n, the formula for my coefficient, c sub n, is just the coefficient, the nth derivative at a over n factorial. And so we get a power series written in summation notation, which we haven't done yet, which takes the general term and lets us write this in a nice succinct method. Now, of course, plugging in n equals 0 and starting through, we get the 0th derivative at a, which is the original function, over 0 factorial x minus a to the 0th. And of course, you again get that triangle trifecta here. The plus the first derivative, we ratchet up n by 1 over 1 factorial x minus a to the first, and of course, so on and so forth. Right? Now, we should also realize that by defining a power series in function notation, each input is only going to map to one sum, right? So if I do something like p of 3, what that really means is take all these terms out to infinity, but replace, and I'll try to show this in color, but replace all the x's with whatever x value you want. In this case, it'd be 3 if I wanted to find p of 3, right? And so we a lot of times define the sum in terms of function notation, so that we use p of x so that we don't confuse p of x, which is the actual sum, with f of x, what's being used to create the sum, which is a little confusing to hear. So let's look at a few examples. Find p sub 3 of x, the third degree Maclaurin polynomial for f of x equals e to the x. Well, this goes very fast because we know e to the x, right? So e to the x is given by 1 plus x squared over 2 factorial plus x cubed over 3 factorial. If I wanted to find p sub 3 of x, what it really means, and I always like to put out this general term here, I think it helps you in the long run, right? So what p sub 3 of x means is in summation notation, usually starting at 0, that you can start wherever you want, with the general term, like so. What do we have to put up here to get this to end in the right spot? We want it to end with 3, so we should probably put a 3 up here. This is the third degree Maclaurin polynomial. And it's all it is doing is just relating what you've done so far back to function notation and summation notation. Okay, so let's go ahead and go further. Write p sub n of x, the Taylor series for f of x, including the general term. Well, this one doesn't want me to just go out to the third degree. This one wants to go out forever. So again, I always start with e to the x. Right, same idea. The more you write it, the more you're going to memorize it. And we go out to here. And then we have p of x. No limitation now, so we don't have to match these together. P of x really assumes that we go out to an infinite degree. But it's going to be very, very similar. We start at 0. We have the same general term, but now we go to infinity. Using a calculator, approximate e to the negative 0.5 using our third degree polynomial. Okay, well, e to the negative 0.5 is basically e to the x, but with x replaced with negative 0.5. So we can do that by taking p sub 3 and replacing x with negative 0.5. And I'll do this in two steps. We can first see it in summation notation of negative 0.5, easy for me to write, negative 0.5 to the n over n factorial. Okay, or we can start writing this out if you would like as well, where we could say that the third degree polynomial becomes, and then we just follow the pattern. We replace n with 0, so it becomes negative 0.5 to the 0th over 0 factorial plus negative 0.5 to the first over 1 factorial. We have a couple more to do, right? Negative 0.5 to the second over 2 factorial. And last but not least, and I'll use a little space over here, negative 0.5 cubed over 3 factorial. And then a little bit of math, but I actually think we can do this math. It's good practice for us to get these fractions in. I think my first term here just becomes 1. Anything to the 0th is 1. My second term becomes minus 1/2. My third term becomes plus 1/2 squared, which is 1/4 over 2. That's really 1/8, and I'll save some space, so plus 1/8. And then the last one, 1/2 times 1/2 times 1/2 is 1/8. So I get minus 1/8 over 3 factorial. That's over 6. And 6 times 8, I think, is 1/48. So what we're saying is that e to the negative 0.5 is approximately this expression. And we could add all that together, but I'm going to go ahead and pull up the graphing calculator right now anyways. I'm going to use Desmos. You should use your graphing calculator. The better you get with your graphing calculator, the more successful you'll be. And we're going to go ahead and see how we did. So pulling up Desmos quickly. If I wanted to get rid of these guys, let's start with e to the, let's start with our actual expression here. 1 minus 1/2, right? Plus 1/8 minus 1/48. 0.604. E to the negative 0.5. 0.606. Look how good that is. We were able to evaluate approximately the negative square root of e just by using 4 terms. Gosh, we are good. Okay, using our graphing calculator, what degree Taylor polynomial is needed to make the values of the function p sub n of x match, or at least have very minimal error, for all x's greater than or equal to negative 2? Well, let's just graph e to the x first. Okay, something like that, yeah. And then let's just start with our function. So we have 1 plus x. That matches pretty well. They said for all x is greater than negative 2, though. So what I'm really looking for is, when does my red graph really perfectly approximate my function from negative 2 on out? I'm just going to keep typing out terms. Might as well. X squared over 2 factorial, right? And actually, that's pretty good right here, but we need to go to negative 2. Plus x cubed over 3 factorial. You know what? I'm sick of writing all this out. Why don't we be more efficient? Why don't we keep our y equals and actually write this using summation notation? Here we go. This, I think, is going to be a lot faster. N equals 0 up to, I'm just going to call this a for now, and you'll see that we'll get to change a in just a second, of my general formula, isn't it? X to the n divided by n factorial. Add a slider for a. Cool. Let's make this one go out to, I don't know, like 100 or so. Start at 1. All right, so we're starting at a tangent line. Let's just make it better. Second degree, third degree, fourth degree, fifth degree. Oh, I think actually you could argue that by the time we get to the, here's the fourth, by the time we get to the fifth degree, we're actually looking pretty good like the function. We can go further than that, but I think, yeah, I would argue that maybe by the fifth degree, our polynomial pretty darn well approximates e to the x. Of course, we could keep going, and the further we go, the more that it's going to approximate. All right. You have a little bit of practice on here. It shouldn't be anything too terrible, and I'm not going to take you through it. I think you guys will do just fine. I'm going to post the solutions as always, but thank you. At this point, you now know all 4 of your Maclaurin polynomials you need to memorize. e to the x, cosine of x, sine of x, and the geometric Taylor series 1 divided by 1 minus x centered at x equals 0. Great job so far. We only have a few lessons left to our power series. I hope you're enjoying.